Hi, everybody, and welcome to our second video on how to make your own beautiful astronomical images. This time we're going to focus on Hubble images, so you can make beautiful processed images from Hubble data that you can enjoy for yourself or give to family and friends. All you need to do is to download raw Hubble data and convert them into a file format that you can use. Hubble actually provides a little piece of software called the FITS Liberator that converts astronomical data files called FITS files into astronomical image files like TIFF files. Once you have the TIFF files, you can just import them into your favorite image processing software and then have fun. If you don't have a favorite image processing software, and even if you're completely new to this, we're here to help. There's a program called Gimp that works perfectly and is also free and publicly available. A few months ago, we taught you how to make images of Jupiter from the Juno mission. In that video, which you can go to here, we taught you how to download Gimp, and then how to download Juno images and import them into Gimp. We also showed a step-by-step demonstration on how to process the images so you can make them into your own. If you haven't seen that video, we recommend that you start there so you can learn a little bit more about Gimp and just image processing in general. Here is the link again. This video focuses on Hubble data and how you can use it to make your own pretty Hubble images. We will be telling you more about the Hubble telescope in general, but with a particular focus on the cameras and the filters that are used to make images. First and foremost, Hubble is a scientific instrument, so I'll be telling you more about why astronomers picked certain types of filters and what kind of astronomical information you can get with them. Then we move on to what kinds of images you can make. We teach you how to download Hubble data and put it in the right format. You get the data from the Hubble Legacy site and use a special piece of software called a FITS Liberator to convert the files into a format you can use in image processing software. We also show you how to use the free image processing software Gimp to make images of your own. As an example, we teach you how to make your own pillars of creation. The video that follows came from a couple of classes that Patrick and I taught last summer. So, without any further delay, Patrick, tell us about Hubble.
So let me go ahead and dive in and explain the mysteries of all of this Hubble Space Telescope and its imaging system. Now, we're all familiar with the Hubble Space Telescope. This is a huge instrument. It has a large mirror right here, which is about 2.4 meters. It's about 95 inches across. This telescope, for you telescope buffs out there, this is an f/24 focal length telescope. So it's not a fast light gathering telescope, but it has a huge mirror and is able to gather light of faint objects. It is equipped with an array of many instruments. This camera, we're going to talk a little bit more about this. This is a wide field camera 3, which was one of the last instruments that was installed on the final Hubble servicing mission to the telescope. Just to give you an idea of the range of wavelengths that Hubble can see, here is the electromagnetic spectrum, and your short wavelengths go down to long wavelengths. But Hubble can see in this range, in the ultraviolet and in the near infrared. And if we expand this, you can see some of the ranges of wavelengths that some of these instruments can see. The wide field camera, which is the main camera on board the space telescope, can see ultraviolet down to a good portion of the infrared. So this is the wide field camera, and it's a huge instrument. It's about the size of a refrigerator. It looks complicated, but basically, if we just boil it down, it's a huge version of a digital camera. Light goes and hits this pickoff mirror, and then it's separated into this two paths. The blue path takes it into the UVis, which is the ultraviolet and visible detector. And then the second path takes it into the infrared detector, which will take images of distant galaxies in infrared or nebula or planets. Now, in front of each of these detectors is a whole array of filters. And this is the important thing for you to remember, is because we're going to go into a little bit more about filters and what they do. So when Hubble takes a picture, the light goes through, passes in front of a particular filter that an astronomer has selected, and only that light hits the detector, and then it's captured as a black and white image with that particular filtered light. The UVis channel has 47 filters and one grism. A grism is like a grating prism, that's what that is. And the infrared channel has 14 filters and 2 grisms. This is what it looks like before they were placed into the Hubble Space Telescope, the filter wheels. Here is a whole wavelength chart of visual and infrared. Here is the wavelengths in angstroms, although we talk about nanometers these days. There are narrowband filters. These are extremely narrowband filters called quads. And then there are regular narrowband filters. And then there are medium band filters. And you can see that the wavelengths, the range of wavelengths are a little bit wider. And then there are extremely wide bandwidth filters. And the names are given by, over here, by an F, and then followed by some numbers. N is for narrow, and you have a medium here, and then you have a 550 wide, and these are long pass and extremely wide. The infrared filters, kind of the same, except because of longer wavelength, they're measured in micrometers. This is the kind of range, but it's very similar to the visible range for infrared.
So I'm going to go through very quickly what you're looking at when you're looking at all these different filters. Now you've had an introduction, you know there are these narrow, medium, and wide filters at different colors, but they aren't just randomly chosen. They're chosen because they have, they have a purpose. And so I'm going to tell you a little very quickly about what that purpose is and why those filters were selected by astronomers to put on the telescope. So we're going to start with this lovely, nice red picture. You've often seen, I'm sure, nebulae that look like they're just all red, and there's a reason for that. And that's because most of the light is, in fact, coming out at red wavelengths. That's because nebulae, diffuse gas, does not emit its light at all colors the way the sun does, a continuous spectrum across the rainbow, but emits its light in what are called emission lines. I'm sure you've heard of emission lines. You probably already know what emission lines are, but just to make sure everyone knows, they are very narrow spikes of light at a very specific wavelength that correspond to different elements and different atomic transitions of different elements in different ionization states and excitation states within an atom. So I'm going to break that down a little bit, but the main thing to see here is you can see this big one in H alpha. H alpha is hydrogen. H for hydrogen, alpha, go alpha, like the main dog. And you can also see that there is a little nitrogen line poking in here too. So very often the H alpha and N2 are together. Those numbers like N2, O3, sulfur 2, represent the ionization state. The higher the number, the more highly ionized. So O3 is oxygen that's had 2 electrons ripped off. Sulfur 2 is sulfur that's had 1 electron ripped off. These others are, if it's 1, like helium-1, then it's a neutral atom. So I know that sort of seems a little backwards. The astronomers have their spectroscopists really, and I'm one, so I can diss them all I want, have the number a little higher. 2 electrons ripped off is oxygen 3, but that's how it works. So you can see the oxygen 3 very strong. The next strongest line is this oxygen 3 line. So what causes those lines to be so narrow? Why does diffuse gas emit like this when the sun, if you break it up with the spectrum, as you've all seen in the by the coelostat, has constant continuous emission with those black lines in front of it? Well, this is why. It's because electrons in atoms are responsible for both absorbing and emitting light, and they do so when they jump from electron orbital energy level to another. So as I know you all know from your quantum mechanics studies, electrons can't be in any old energy level around an atom. They are discrete, different energy levels where electrons are permitted to exist. And just like going up the stairs, unless you're like a ghost or something, you actually have to step on this stair, and then that stair, and then this stair. You don't just continuously slide up the stairs. It's a very similar for electrons and atoms. They can only be on one stair or another, or in the process when they're making a transition, there's a little probability of oscillation between the two, but no energy level in between. So you can see that the difference in energy levels from each of these, and you can see the N equals 1, 2, 3, 4, 5, when an electron in an atom is excited, and then just because of entropy and because all hot things cool, those electrons cascade down. They drop down to lower energy levels. And when they do that, they emit photons of precisely the energy and therefore the color associated with the energy difference between those two wavelengths. So you can see on the right here, these are all the hydrogen atom levels. They actually have lovely names like Lyman, Balmer, and Paschen. And if you look at those wavelengths, you'll see that they correspond perfectly to ultraviolet, visible, and infrared wavelengths. So some of those filters are deliberately chosen to be narrow filters to just isolate that one line and tell you, oh, I want to look at highly excited oxygen, or I want to look at neutral helium, or I want to look at excited hydrogen, or whatever it is that you want to look at. You select that filter to isolate for those lines. So if you're going to do something that's like a nebula, then you're going to want to have those narrow filters. So we spoke a moment ago about continuous spectrum, where you've got all the colors of the rainbow. That comes from solid things like, let's say, the core of a star or a filament in a light bulb. If you're looking at gas, because the gas is so diffuse, and each of these atoms has sort of all these nice discrete electron orbital levels, then you get this line spectrum. If you put a gas in front of a hot object like the sun and its atmosphere, then those exact same wavelengths are not an emission, but are an absorption, because the light comes from behind and causes those atoms to jump up precisely that energy amount. So emission lines are what happens when an electron drops down a level. Absorption lines are what happens when an electron jumps up a level, but always exactly at that same wavelength, corresponding to the energy difference of those two electron levels. That is the spectroscopic background between emission lines, absorption lines, and continuous sources. So what you select depends on what you want to look for. As you can see, the broader band filters, like these, are the standard UBV. Juan, I see you raised your hand. Go ahead. Is this a question about what I just said?
Yeah, actually, I was wondering, like, if I wanted to highlight the presence of water in a nebula, do I look for filters in the emission spectra of individual elements in the water molecule, like oxygen and hydrogen, or does the molecule as a whole have different emission?
Molecules have different lines. These are atomic lines. And that is, most molecular lines, by the way, are in the millimeter radio wave, because they're bigger, sluggisher, more the transitions, which have to do with the vibrations and rotations and stretch of a molecule, are different. These are atomic transitions. Okay. So just finishing up, if you're looking at stars and you want to pull out stars, you choose one of the broader filters. And as you can see, U, B, and V, which stands for ultraviolet, blue, and visible. If you have hot stars, like the star at the top, you've got a lot of ultraviolet, much more ultraviolet than red. But if you've got a cool star, then you have more red than ultraviolet. So you can, by selecting which filters you use, you can isolate, are you looking for hot young stars? Are you looking for the cool underlying older population of stars? So it really just depends what you want to see and what the astronomers want to pull out when they do these images.
This image is taken by 7 different types of filters and composited. So when you're looking at not only visible light, you're looking at ultraviolet and infrared. And you can see here, there's a kind of wide band ultraviolet, there's a little medium band. In the visible, there's a kind of shorter band and a very narrow band in the red. And then you've got these wide band infrared images. When you look at Hubble images, it's telling you a lot of useful information about this particular object.
The ultraviolet ones in pictures 1 and 2 show where the hot stars are, because that's where they're broadish looking filters. You can see the width of the filters are broad. They're looking for stars that have ultraviolet coming out of it, which means young hot stars. In the visible, there's that oxygen 3 that I mentioned. That is everybody loves oxygen 3. It's right there in the middle of the visible spectrum, and the very narrow H alpha filter. So that's showing you ionized hydrogen gas. And then the longer wavelengths are the cool stars. So you can see in each of those images, 1, 2, 3, 4, 5, 6, 7, different things are coming out. The hot stars, the ionized nebulae, and the underlying population of stars. And so when you combine them all, you get that in that middle snapshot, a beautiful representation of all of those different physical things happening at the same time. Are there any questions on what I just shared with y'all? Yeah, Sarah.
So I guess it's a nomenclature question. You've got oxygen 3, which is 2.
Doubly ionized, yeah.
Right. But hydrogen alpha is neutral?
Well,
or 1 ion?
What you're seeing there, that's a great question. And I did gloss over it, and bless you for pulling it out. Because it's a tracer of ionized gas. But what you're seeing, since ionized gas has no electrons, it's just plasma of electrons and protons, is the act of capturing an electron and then that electron cascading down. So in order to get that cascade down, it's going from being ionized to being captured. And so it is a tracer, even though you're watching the actual transitions within a neutral atom because the electron is now captured. Right. What you're seeing is the act of it being captured and then cascading down. So it is a tracer of what we call H2 regions and not H1 regions, because it's ionized gas that is getting where the electrons are being captured and cascading. And believe me, it'll get ionized in a second later anyway. Thank you. That was a very sharp pickup there, yes.
So when you see those press releases, do they really represent the color that we see with our eyes? Well, actually, not exactly, because the purpose of the Hubble pictures is to provide information about the objects. Now, there are 3 different types of images, and one is you use natural colors. If you use wideband filters, mostly invisible light, then you're going to get an image that would look like what we would see with your eyes. For instance, blue, green, and red here. And it's mostly covering almost the entire part of the visible light of the spectrum here. There's another type of image. It doesn't even have any filters in invisible light, and they call this image a representative image taken by 3 different types of infrared filters or even more. Of course, we can't see infrared light, so to make this visible, what the astronomers have done is they've taken the shortest infrared light and mapped it to blue, and they've made the middle one to green and the longest one to red. And then you get an image of Saturn that looks like this. But what we're really seeing here, we're seeing Saturn represented in colors, kind of infrared, but representative colors, to tell you the color differences of the cloud tops of Saturn. There's another type of image, which is enhanced color. You would have 3 different narrowband filters, but they're all in different shades of red. So in order to differentiate them, we basically have to separate them apart in using the visible light colors. All right, so we finished off with these different representations of pictures from Hubble. More importantly, is to know the range of wavelengths for each of the different parts of the spectrum that are used to take these images. So you've got ultraviolet and your visible range, and then your infrared range. So we're going to look at an image, the Eagle Nebula, which was taken in all visible light. This image was posted back in the mid-90s and looks like this. But this is not what it looks like to your eye, because if you were to take the actual colors, this blue one is actually green. I marked it here, and these 2 are actually red. And so they just made it red, blue, and green, and then came up with an image like that. If you were to make this image with green and 2 shades of red, it would look more reddish than this image. This is an image taken by the European Southern Observatory, which is nothing like this. So here is the Hubble Legacy site that you'll go into. And when you go into that site, you can type in Eagle Nebula, for example, which is what we're going to process today. And you'll get these images, a whole bunch of images. You can see the file name and the filter number. There's one here. Look for similar images. There's one, there's another one, and I think that, oh, this is the 3rd one. These are the images that you want to download. All the images that you get from the Hubble Legacy site are in a format that you really can't use in a normal photo editing program. So when you go to the site, you're going to see file names that look like this. So what do these file names mean? Well, take note of the filter number. So there's an F673 narrowband. All the files that you download for your images should have a SCI, which stands for science.fits. So how do we make these fits in something readable that you can use in say, Gimp or even Photoshop? Well, you need a program called Fits Liberator, which will translate your images into a TIFF, and then you can bring them into GIMP.
Fits Liberator is a piece of software provided by Hubble that lets you convert astronomical data files called FITS files into standard image files like TIFF files. Here is the Fits Liberator website where you can download the software.
It works for all PCs, but it only works for Macs with OS 10.11 through to 10.14. If you are a Catalina or Big Sur user, there is a short video at the end that shows you another way to convert FITS files into images. So we're going to go and go to the site, enter here. Eagle Nebula is also known as Messier 16. So if I type in M16, I'll search, and I'll get a whole bunch of results like this. You want to click on images, so you can show all the images on this site. If you want to do advanced search, you can do this, and you can pick your instruments. But the images that we're going to pick today are these three images: this one, and this one. And what you want to do is, where you see download data, just right-click. I'm using Windows here, Windows computer. Go ahead and say Save Link As. And then you can see the whole file name, the filter number. This is F502, sci.fits. And I've actually downloaded all three here. So to save time, because this takes about 5 minutes to download, 200 megabyte image. So the images will look like this once you've downloaded FITS. It'll show up as an icon with a portion of the Eagle Nebula icon if you're looking at in a large icon mode. And so we're going to go ahead and start with the first filtered image, which is filtered 502 in a narrowband. And once I open up FITS Liberator, it will look like this. It'll come in as an image, and you're probably wondering, well, where is it? So in order to make this visible, we have to go to this area where it says stretch function, and there's a whole range of stretches here, and they're all kind of mathematically, the mathematical functions. But the one that seems to work best is this one, which is the log x. And I'll go ahead and do that. And now we've actually stretched it and spread out all the pixels. And if we take this cursor here, which is the black level here, we can move this around and move this, the white level closer, make it the image brighter and brighter, and then we can then see the Eagle Nebula. And you can just adjust this until you get a brightness that you really like, say about here. Right, basically it's enhancing details that otherwise wouldn't be seen with the original picture. I'll save my file. Save file. Save it in this. And you can see the extension here is .tiff. So save. I'm going to open up the next one, which is this one. 657. And again, it's the same process. It's almost invisible. So let's go ahead and stretch that out. X. And this one is a lot more visible. You can adjust these ranges as you wish. Save this one, looks good. So it's really up to you to choose the stretch so that it looks kind of okay to your eyes, so that it could be processed into a nice color image.
is that 3 different images that you're stretching? I know you've already saved them to your computer. Is it this? Did you pick 3 different ones, or one that you're putting in 3 different ways?
3 different wavelengths. 3
Yeah,
different images at 3 different wavelengths. Yep.
Also, can I ask, can we use Photoshop again, or do we need to use Gimp this time for the image processing?
You can use Photoshop. Okay, so we have 3 TIFFs that we just saved out of FITS, and we're just gonna put them into Gimp.
Gimp is the free downloadable image processing software that I mentioned earlier. To get Gimp, just go to their website and download the version that is appropriate for your computer. There is a lot more information on our video about how to make your own Juno images, so go see that video at this link here.
We're just gonna put them into Gimp, and so all you have to do is just drag and drop. I'm gonna rotate it so it's the right way up. So I hit rotate. Next one, bring in. So here we have them, 673, 656, and 502. So we're going to make these images red, green, and blue, but to help you keep organized, if you right-click on the first image, which we're going to make red, we're just going to color tag that red in this menu here. So click on the second image, we're going to make this green, and we're going to color tag that. Right-click, color tag green, right-click on this image, color tag that blue, and we'll make sure that our mode is in red, green, blue. There we go. Otherwise, we won't be able to colorize these images in red, green, and blue. So for the red image, we go to Colors. We go down to Colorize. And for the hue, we're going to make this into a all red image. On this hue scale, red is at 0. We need saturation at 1 to make it nice and red. And it's too much, it's too bright, so we're going to make it, turn the lightness down to about 0.5, negative 0.5.
And of course, these are the things you can play with to get your image to look the way you want. What is the hue, how saturated is it, so forth.
Okay, and for the green, we're going to do the same thing. Down to Colorize. And green is about 1/3 on this scale, so about 0.33. Saturation at 1, lightness at 0.5, same as before. Minus 0.5, sorry. Okay. Blue. Colorize. And blue is at 0.66. Still. Saturation the same as before at 1. Lightness down to -5. And okay. And when you look at this, nothing has changed, and the reason is that this layer is obscuring all the colors from the 2 other layers, so the green and blue don't show. So what you want to do is go to Mode and go to Mode is kind of like the blending mode, and if I hit the down arrow, I have a whole bunch of blending modes, and the one that we're going to choose is Screen, which allows the green. Screen is like a projector. If you have a projector that projects red light, and then you have a second projector that projects green light, then you get a mixture of green and blue, which gives you these yellow tones. So we're going to do the same with green, sorry, and we're going to change that blending mode to Screen to allow the blue to go through to green and to blend with red. And there you have a nice color image. of the pillars of creation, and we go to color and go to curves. You can start adjusting the colors. So if you have, say, too much green, you can always reduce the green. And so when you click on these curves, you make these little edit points, and you can change them any way that you want. But it actually selects certain parts of the green in the image. So I think in this one, this part here, I raise it up, affecting just the brightness, the brightest green pixels. You see that there's a little, over here, only the brightest portions of the pixel levels of green at this point are showing up, and everything else around the image, all the other greens are gone. If I were to raise, say, the greens in this lower level here, I'll get a lot of green. So you can actually select pixels of green in certain parts of the image. So you can adjust these so you can get a nice kind of shade of green that you want. So you want to save your project first of all. So if you go to File, Save, and it will save as your project in Gimp as an XCF file. So that's so that you can go back to it, and then you can readjust your curves and all of that stuff. But if you want to save out this image, go to File and go to Export As, and it will export. It will export as a TIFF because it says .tiff, but you can change this to, say, a JPG, like a JPEG, and then just hit export. So that's all you have to do. It'll come up with, well, I've already exported as a JPEG, but it'll give you an export, and you can just say you don't want any compression, and then just say export, and you save your image. Okay, well, that's it. So you have everything you need to create those beautiful images.
That's right. We asked the students in our class last summer to create some images of their own, and this is what they came up with. So there you have it. We hope you have a lot of fun making your own Hubble images, and you can use them to make gifts, cards or pictures or anything for friends and family during the holiday. So put your new skills to use and have a good time. Patrick, any final words?
I hope that you get a lot out of these tutorials, and work with some of the best images from the Hubble Space Telescope.
All right. Thanks so much. Happy holidays, everyone.
If you have a Macintosh with OS Catalina 10.15 installed, here's another way you can turn your FITS files into TIFF files using this software. So you're going to go to this site, you just hit download, and then in download, there's a number of selections. And for the Mac users, just go to Mac. And there's various downloads for Catalina. There's a 1050 Aqua Catalina, and there's a X11 and 15. It's either one of these two if you have Catalina. So if one doesn't work, download the other one. You're downloading this one, a DMG. That should be pretty straightforward. And of course, for Windows, I would use this one, Windows 64-bit. Now, once you've done that, you'll have an icon that looks like this, SAOImage. And if you double click on it, this is the software, and this is the window that you'll see. So how do we load something into this? Basically, it's a FITS reader, just like FITS Liberator. How do we load something into it? To load your image, you go File, Open, and navigate to the directory that contains your images. Go ahead and load one at a time. And what you see is absolutely nothing. That doesn't mean there isn't any information there. There is. We have to do stretching on it to make the image visible. You want to make sure that your whole image is visible in the entire window. So if you hit zoom fit. That's just like, your PDF. You want to fit your whole page in. Then you want to go to scale. We're going to bring up two windows here that we're going to be using to make adjustments to the contrast and also the amount of pixels. One of them is scale parameters, which is kind of identical to the FITS Liberator, which shows you your histogram of all the pixels. This is the distribution of all the pixels in images from the dark shadows to the brightest pixels. So you can see the limits is in a negative range, and the high is where this green line is. So you want to bring that box up. And then the other thing you want to do is go to color and go to color parameters. And this is where you can adjust your contrast and your bias. And you'll see what happens when I use the bias. So how are we going to make this image visible? Well, we're going to go to, in this menu here, there's all these rectangular buttons, which are the same as these, but I tend to want to use these because they're kind of easier. I'll go to scale, and you see the same kinds of stretches that you saw with FITS Liberator 3, although it doesn't display all the formulas. And you can just go through these. Make sure it's in minimum and maximum. This just basically defines your minimum, maximum pixels according to this histogram. And then just go through these. So linear really doesn't do much. Well, now there's a good one. So usually in these images, if log seems to work out the best to bring out some detail. Now, if you want to make some adjustments, if you were to bring this line for the high values and restrict it, limit it, you're actually restricting a lot of the pixels just to the right of the line, and you make your image kind of washed out. Usually, you should put it somewhere where the curve just begins to grow. And then once you've done that, you get this gray kind of image. So you want to make it a little bit darker. So all you have to do is just adjust your contrast. If you want, you can adjust your bias, although you are lightening up the background and bring out some of the stars in the background. So just basically play around with these. You don't want to blow out the center of this if you want to see detail too much. If right now it's basically blown out, so you might want to just back off on your contrast and then adjust your bias and darken the image again. And if you're happy with that, all you have to do is just go ahead and it is File, Export. And here, unlike FITS Liberator, you can output a JPEG or a PNG.